Hi, so my name is Felix, and this is Rocket. And we're going to make a short presentation about some of the recent work on embodied language learning that has been done at DeepMind. So the goal of the grounded language team at DeepMind is to work towards models that exhibit convincing embodied understanding of language as it pertains to the external world. Ultimately, we would like to develop learning systems that can do the sorts of things that you see in the image, interpreting instructions given by human users and responding both by carrying out the necessary movements to get things done and by producing useful language responses. Now, one way of going about this challenging endeavor is to break it into separate subproblems. For instance, we might study the language processing part of the problem, or the motor control part of the problem, or the visual recognition problem. Of course, breaking things up like that has led to some incredible developments of techniques that will almost certainly be important parts of solving the wider problem as I posed it previously. Those include really powerful language models, flexible algorithms for learning control, and increasingly accurate large-scale image and video recognition. But while we intend to lean greatly on those advances, the approach we're going to take here is a little different. And I think it's beautifully motivated by a paper that's been very influential to me. More is Different. It's a 1972 paper in Science by P.W. Anderson, who's actually a theoretical physicist. So he argues convincingly that we may never entirely understand or explain complex phenomena by explaining each of the constituent subparts of the phenomena in isolation, however precisely we explain those subparts and however well we model them. Now, one reason to agree with Anderson on this one is because he was a Nobel Prize winner. But another reason is that some recent empirical observations seem to point in this direction. So this is some work we did to really underline the fact that there are important differences between visual question answering and the full embodied question answering that's been studied by some interesting papers in recent years. To see this, consider two different setups. So firstly, a visual question answering task where the question is just something simple like which side is the red guitar on? And then the answer is either right or left. So super simple visual question answering task. And of course, a good baseline model for a task like this might be a basic language encoder whose representations are concatenated with the flattened output of a convolutional network. And then a small connected layer leads to an output where the model just has to make one of two different predictions. But also consider that we're not just interested in optimizing the performance of this model on some training set or on even some held out set of questions from the same distribution of the training set, but instead we're interested in measuring the combinatorial generalization of the models. So in particular, we're going to train them on only some of the possible instructions for the different things that the model might be able to see. So in this case, we might train it on red cup, red guitar, and green ball, but we won't train it on green cup. And then we want to measure how well the model identifies green cups, given that it's experienced each of the words green and cup in different contexts, but it's never experienced them together. So when we do that with a simple, not particularly well-tuned model, as I just described, notice that that model gets about 97% accuracy on the training set, but only about 78% on the held-out instructions, the held-out questions. But we can also consider a fully embodied version of the same problem, where instead of getting a question, the agent gets an instruction, and it has to predict many different small movement actions which take it towards the correct thing, and then it activates the correct thing by just bumping into it. And we can, at a high level, apply exactly the same test of generalization. So rather than asking questions about an object, we're giving instructions about those objects. But in the training set, we're going to have the same set of questions or instructions referring to different color and shape combinations. And in the test set, the same set of held out color and shape combinations. And also importantly, we're going to keep the architecture exactly the same, except for a small difference in the final layer, where in this case, the agent must choose one of 8 sort of relatively fine-grained actions rather than those 2 absolute directions, left or right, when answering a question. Now, when we do this and consider how well the model generalizes, we observe some very interesting things. First, note that the agent that can move actually learns the task in fewer samples. This is fewer exposures to raw images, not fewer episodes. And that's despite having what you might consider to be like a more difficult learning challenge ahead of it. Now, this is probably because it can get really close to objects, so it's simply easier for the model to learn about their important visual features. Another important point is that if it's uncertain about what an object is, it can always move closer to it to sort of check and increase its certainty. The most interesting result here, though, is the performance on the test set, which could be considered a measure of the systematicity of the architecture. But of course, we've seen that in both the visual question answering and the embodied question answering scenario, and the embodied agent instruction following scenario here, the architecture is exactly the same. What we find is that the agent that can move around and walk up to the objects and collect them actually generalizes, in this case, with 100% accuracy. So there's a really big difference in the systematicity of the same architecture in these two different contexts. Now, one way of explaining this outcome is to simply consider that the agent has much richer training data because it's seeing the object from many different angles, including up very close, as it learns. So you could say that it learns better representations which allow it to generalize. But another important thing to note here is how uncertainty might manifest itself in the two different types of model. So even if the embodied agent has some uncertainty and makes some incorrect predictions in a given episode, it doesn't necessarily score a failure on that episode, right? It can easily recover. It has to make consistently many different individual actions and get them wrong consistently across an episode in order to actually end up bumping into the wrong thing. Whereas the VQA model only needs to have sufficient uncertainty to get a particular single prediction wrong on the test set. That might be another way of explaining why generalization is different in these two cases. Now, it's not just the fact of embodiment and instruction following per se that can affect the apparent systematicity or generalization of the system. Given two instruction following agents that can both interact with their environment, the particulars of the environment can also play a big role, as we showed in the following experiment where we compared the same architectures when trained in a 3D Unity room and a 2D grid world. So in each of the two environments, we can create episodes in which there are 3 movable objects sampled on a per episode basis from a global set of 10, and also a landmark object which can't be moved and is always the same. The initial locations of all the objects and the agent are randomized in each episode. And in both cases, we can instruct the agent to carry out one of two types of behavior. So in the 2D environment, an instruction might be something like lift a cross. And in that case, the agent must move towards the cross and take this specific interaction action. If the agent is something like put a cross on the bed, then the bed is the single stable object which appears in every episode. And the agent must go towards the cross and then make the interaction action, then move towards the bed and then make the uninteraction action and leave the cross there. In the 3D room, the tasks are similar, but the object manipulation is much more fine-grained. So there's 16 relatively fine-grained actions, which allow the agent to kind of rotate the objects, lift them, put them down, and of course move its body or its field of view. As before, we can not only consider the score on a training set or some test examples from the same distribution as the training set, but we actually are interested in combinatorial generalization. How systematic are these models when they learn? And in particular, we train the agent to lift in both environments all of the objects in the global environment set of objects. So it knows the name of all of the possible objects that it might need to interact with. But we only train it to put some of them on the bed. So this is another test of held-out generalization. And importantly, we can have exactly the same distribution of instructions in both of the environments. As before, the agent architecture is entirely similar in both conditions. Apart from minor details like the action space the action spaces are different, so the agent has a different output there. What we see on the left is that the agent performs really quite well when generalizing these putting tasks in the 3D environment. But if we play the video on the right, we will hopefully see that the agent exhibits quite a lot more uncertainty in this case. So here it's not quite sure how to put the object down on the test set, but it gets there in the end. When we look at the numbers, we see that there's really quite a big difference between the ability of the two agents to generalize systematically in these two conditions, even though the vast proportion of the architecture is the same in both cases. We actually did some work to understand this phenomenon because it was quite surprising to us. And we found that the most critical factor at play here is precisely the egocentric nature of the agent's perception. To show this, we can actually turn the 2D grid world from an entirely allocentric environment into an egocentric environment. And we do that by putting a window around the agent's field of view, such that the agent always remains in the middle of that window. And when we do that, we find that a large amount of the deficit in generalization error between these two environments is actually removed. So this tells us that it's really egocentric perception that can provide some useful invariances for how the agent sees the world, and those invariances can potentially represent a useful bias which allows it to generalize better with respect to instructions which require the agent as a sort of entity and as a self to interact with objects in the world. If you're interested in exactly thinking about why there might be differences when we have an egocentric scenario, consider also the range of different states which look the same to the agent when it has an allocentric view as when it has an egocentric view. Now, in the previous experiments, we considered the ability of agents to generalize productively to instructions that contain novel combinations of familiar words. But how can we develop an agent that is robust to entirely new words? For this purpose, we leverage the power of unsupervised learning, and in particular, by embedding instructions into the rich representation space acquired by large predictive language models like BERT. With a pre-trained BERT model installed as the language encoder in an agent, we can then train it as before on manipulation tasks in the Unity environment to follow synthetic template instructions generated by the environment. Notice that when we do this, we don't backpropagate into the BERT weights, because a lot of training is required, and that would degrade the quality of the BERT representations over that vast amount of training in the environment. However, as the agent learns, the remaining agent weights obviously have to adapt to the goals as they are specified in the BERT embedding space, rather than in an embedding space of a different language encoder. And then once we've trained the agent in that way, to evaluate its robustness, we get test instructions from unsuspecting lay human users. Now, there's some important details about how we get those instructions, which I'm going to talk about in a minute. But it's also important to remember that there's loads of architectural choices that can be made when considering how best to integrate BERT into an agent like this. So remember that BERT doesn't return a single representation of the instruction. It actually returns lots of contextualized embeddings of the word pieces in that instruction. One way to integrate those is just to pull them together. But another way is to have an additional self-attention layer, which is actually learnt as the agent interacts in the world. You could think of that as an additional final layer of the BERT representations, where as the agent gets to know its environment, it learns to modulate those representations into a space which is most useful for it. And of course, when we combine it with the vision, we can add in the visual objects in the form of the superpixels coming out of the visual encoder and integrate those into a single multimodal self-attention layer in the spirit of recent work like Vilbert and things like that. So when we do that, we can evaluate whether or not the agent responds better to robustly to held out human instructions. Finally, something else that we found very effective was to inject noise into the template language instructions, the environment language instructions, as the agent learns, just while it's training. So this is just a basic noise model where the probability of a typing mistake corresponds to some degree to where the different keys are on a standard keyboard. Because in our experiments, we have humans actually type the instructions which get passed to the agent. So the way that we got the instructions was one of the interesting aspects of this work, because rather than just getting humans to paraphrase the template instructions that came from the environment, we instead actually got the humans to go into the environment and give the instructions based on what they saw. Now, we didn't want to prime them, so we made all of the objects that they might need to refer to red, and we made the sort of landmark objects that they also need to refer to white. And then we told them to choose one of the red objects and instruct somebody to basically put it on top of one of the white objects. And that way we got quite a diversity, particularly of the ways in which the people in the raters chose to refer to objects. So you can see that there's some quite wacky stuff going on, and people actually interpret those 3D game objects in quite different ways. So this is a tennis racket officially, but of course somebody quite reasonably thought it was a mosquito bat. And here it's there's actually a toy helicopter in the room, but the rater instead thinks it's, well, initially one rater thought it was a toy fan, probably because of the propeller, and then another rater thought it was helicopter. It is a helicopter, but they spelt it helicopter, which is the sort of thing you might expect if you're dealing with people whose written English is not advanced. So it's very important for models to be robust to this sort of English, if at all possible. And so in that sense, they make useful additions to our evaluation set. What we found then, of course, was that the different ways of integrating the BERT language representations into the agent led to quite interesting differences in performance. So we can do things like compare models that just use the bottom layer representations from BERT, which are a little bit more like traditional word embeddings, or we can consider models that use the full stack of BERT contextual representations. And we can also do things like compare whether we have the typo noise or not, whether we have the multimodal attention and things like that. The best model that we were able to train in terms of performance on the held out human instructions was actually one that included typo noise, it included multimodal self-attention. And remember that the word piece encoding of BERT is actually very important here, because with the typos, the combination of word piece encoding and typo noise are important for the model to get a sense of the similarity between a typo and the intended word, and therefore to learn to be robust to typos. Interestingly, we found that our best model, the performance of our best model, was not that far off in answering these test instructions, the performance of humans, in the sense that we gave the test instructions to other humans. And this is an indication, so humans are only at about 70, just over 70% performance when executing the instructions of other humans. And this is an example of how humans, when they do give instructions, can be quite not particularly well specified, or there might be ambiguity in terms of how they describe the objects they're looking at, things like that. So we think this performance of the best model here actually represents really quite surprising ability to transfer knowledge from text to the grounded, simulated world that these agents operate in. And just to give a better sense of the agent and how robust it is to those instructions, take a look at this video. So here, the agent's getting human instructions correct, even though there was a typo, there was a P in the word boat. Here, the agent's going to fail because unfortunately, the person referred to the keyboard as a Casio, and it just didn't seem to be able to deal with that. Here, the agent eventually succeeds. So the person referred to the train as a tractor, and the agent seems pretty uncertain, but eventually it obviously thinks that tractor's the most likely referent there, and eventually does get the tractor into the right place. So when developing agents that can learn from the world around them, I think there's a lot we can learn from the way in which models like BERT extract knowledge from the text around them. So it's not just the precise knowledge from the text that we might want to transfer from the world of language learning into the world of agents. I also think the BERT objective is very instructive in how well it enables language models to learn very good representations. One of the key insights from the BERT objective is the power of infilling or prediction in building representations. Of course, the idea of building knowledge into a model through the medium of prediction has a long history in AI and neuroscience. And it can be traced back at least until the work of Helmholtz on perception. So in the 80s, Rumelhart and McClellan proposed a model for understanding the perception of letters in words. And then Ellman wrote a very famous paper on language learning, where the objective of the model was precisely to predict the next word. And he showed how much semantic and syntactic structure can emerge in a model like that. And then finally, into the 90s, Rao and Ballard were explaining particular properties of receptive fields in vision by computational models based entirely on predictive coding. More recently, a body of work on deep reinforcement learning has found that auxiliary predictive objectives can lead to agents having much better performance, presumably because they improve the quality of the internal representations in the agent's memory. And they endow them with additional knowledge that in some cases is task relevant and allows the model to perform better. So there's a bit of a deep mind bias in the examples I've chosen to highlight here. There are also lots of other studies that had successes with ways to increase the world knowledge in an otherwise model-free agent. Now, given that there are now various competing approaches to improving the knowledge acquired by agents, in some recent work led by Abhishek, one of the organizers of this workshop, we investigated the use of embodied question answering as a means of quantifying the general or even propositional knowledge acquired by agents as they explore environments in an otherwise task-neutral way. So to do this, we coded up the environment to generate episodes with different arrangements of objects, but otherwise a lot of randomization as in all of our environments. But also to produce template-based questions that make sense given the objects in the room and have a reasonable distribution of possible answers. So you can see from here that the questions that we produce in this data set are broken into different categories, including those that can be answered from a single frame, like what color is the cup, or those that refer to the relationship between objects, like what is the color of the mug near the table, or those that require the agent to explore and remember details about its entire surroundings, like how many balls are there. There's a bit of a flavor of the clever data set in these questions, but they obviously have this imperfect information aspect that you don't get in clever. And importantly, because we're interested in embodied question answering, not as an application in itself, but as a means to quantify and evaluate in a kind of BERT-style way, the knowledge building algorithms that are applied as an agent learns, we did not train the agent directly to answer the questions. Instead, we trained agents with different knowledge building algorithms simply to optimize a question agnostic objective to visit as many objects in the room as possible. So that way we can be quite sure that plausibly in the agent's experience, there is enough information to answer the questions. The question is, does the agent retain that information, even though it's not immediately in the agent's objective to do so? So as the agent learns the policy of moving around, the knowledge building algorithms, in theory, should give it that knowledge, and in particular based on predicting future states. To probe the content of the information that gradually aggregates in the representations of an agent, we simultaneously train a question answering decoder whose inputs are the words of the particular question that's proposed by the environment for a given episode, together with the memory state activations of the agent. Note that we do not backpropagate through this question answering model back into the weights of the agent itself. So the agent is not learning to answer the questions. It's learning to aggregate knowledge, and then we see whether questions can be answered from its knowledge. Now, to score a given agent in this paradigm, we simply run it for a number of episodes and count how many of the trained question answer decoder returns are correct. Here you can see some example episodes of the agent doing its exploration thing. It visits each of the objects as it's trained to do so. And over the course of the episode, the question answering model that is appended to it becomes more confident in answering the question provided by the environment. So we take as the answer that we're going to use to score the agent the response at the final step of every episode. And here's a different question. What is the aquamarine object? So the answer is grinder. So it's like a pepper grinder. And eventually, as the agent moves around, it gets more and more confident and is able to make the prediction. So here is an example of some results on one of the categories of question. The green line is actually the score of the agent when you do backpropagate into the agent weight. So this is the sort of embodied question answering score when the agent can be actually optimized to answer the question. And you can see on these particular types of questions, it does very well. But the score, the line we're interested in is the purple line, which is a model which doesn't have answering the questions as an objective, but it does have an algorithm which allows it to aggregate the maximum amount of knowledge. And in some sense, this is evidence that the agent is getting a bit like linguistic knowledge naturally into its weight, or propositional knowledge. And the algorithm that does the best on these sorts of evaluations is actually known as SimCore, which is an algorithm developed in DeepMind in different work. But the objective is basically long time step overshoot. So the agent with a SimCore has to, conditioned on its memory state, make a prediction about what it's going to see at a large number of time steps, up to say 20 or 30 time steps into the future, conditioned only on its memory state at a particular point, and also conditioned on the actions that it took in order to get to that point in the future. But importantly, it's not conditioned on the observations at those points. So it has to get better and better at sort of inferring from a set of actions what the world is going to do at a certain point in the future. And another important difference here is the difference between SimCore and an alternative algorithm, which does the same sort of long horizon overshoot prediction. And that's action conditional CPC, which rather than using a density estimation generative objective, it uses a contrastive objective, saying whether or not the observation is indeed the observation the agent saw or some other observation. And the contrastive objective doesn't give the agent the same strength of representation to allow it to answer a wide range of questions, as you can see across the range of different question sets that we propose here. So, coming to the end of the talk, but just to summarize, I want to remind you that our goal in this work is an embodied agent that exhibits a credible understanding of language, both by following instructions and eventually by responding with language. And to do that, it's going to need to be able to build up and aggregate the knowledge in its internal states in order to have the answers to the sorts of things you might ask it about. So the results that we've looked at indicate kind of a positive outcome, which is that learning to use language might actually become more and not less achievable as the environments that we're able to train our agents in get richer. So this is an example of the more is different principle that Anderson first sort of elicited in the 70s. Another important point that we've demonstrated is that unsupervised learning from raw text can actually lead to knowledge transfer into an embodied agent, which can make agents more robust to the ability to follow instructions that contain entirely novel words that it's never been trained to deal with. So transfer learning is possible from text to the embodied world. And finally, we've shown how predictive objectives, and in particular long horizon overshoot style predictive objectives, can really enable agents to acquire richer internal knowledge of their environments. And it might be that we need agents to have that sort of knowledge of their environments if they're going to be able to do things like use and command language in a way that allows them to answer questions and provide knowledge to users. So I just want to finish up by saying thanks to a large number of amazing collaborators who've helped contribute to this work, and a little screenshot of the agent having a bit of fun putting planes on beds. So look forward to discussing this work and any other questions about embodied language learning and question answering with you later.